Welcome back to gluten-free learning. Today we are going to be studying numerical methods, and we're going to be looking at the Gauss-Seidel method in this video. So what is the Gauss-Seidel method? Basically all it is another way of solving simultaneous linear equations. So we already know Gaussian elimination, right? We can already do the same thing with that, so why do we even need to know this? And I mean, I don't know. We just got to know it because we got to learn it. It's in the curriculum, and it is pretty easy. I think it's easier than Gaussian elimination, and it could be more efficient for larger matrices, and it can control round-off errors when you get larger matrices too, right? So there is a use to it. I think it's easier. So let's just do it, and you can decide for yourself which method you like, but I think it is a little bit easier than Gaussian elimination, and it's kind of straightforward. And I guess for computational purposes in like MATLAB or larger computer programs, it is a bit faster. So if we have a system, AX equals C, we want to find, so in this method, I'll just run through a little proof, and then we can do an example, and you can see how effective and easy this method actually is. So for a normal system, let's just look at like a 2x2 for this purpose, because it's easy and you get the idea, and then we'll do a 3x3 example. So any given linear equation has this basic form. So there's our first equation, a1x1 plus a2x2 equals c1. So there is our equation. We have a1x1, a2x2 equals c1, a3x1, a4x2 equals c2. So that's our system, and now we want to solve for our solution vector using the Gauss-Seidel. So how do we do that? Basically in this method, it's iterative, right? So first we want to solve for our x1 in our first equation. So just considering our first equation, we want to isolate for x1. So rearranging and solving for x1, that equals this. So you guys would agree, x1 equals c1 minus a2x2 all over a1, right? We just rearranged our first equation and solved for our x1. And now we want to do the exact same thing with our second equation and solve for x2 now, because we're doing the second equation solving for x2. So rearranging, we got x2 equals, so now the only trick at this step is that we just solve for x1, right? We've got a new value for x1, so we just have to make sure that we plug that new value that we just calculated in to our x1 function. So we're always going to have an initial guess. So forgot to mention with this method, you can either choose an initial guess, say of 0 and 0, which is pretty standard in the textbook. You can just choose 0, 0 and do as many iterations of this process as you need to get the solution to converge. But if you know the physics of the problem, if it is a physics problem, then you can kind of get a better estimate of what the correct answer is going to be, or your teacher on your exam or your homework or whatever will give you a first iteration, which I will do that in the example. I'll give you the first, your first guess of your solution vector, and then you'll see that the solution does converge, and it also has a chance to not converge. But we'll talk about that later. So basically right now we needed to solve for our x1, which we've done, and our x2. And then in our x2, we have to put in the updated x1 that we have just solved for. And then this will give us a solution vector of x1 and x2. And then when you have the solution vector, you need to check the relative error and see if it is within your acceptable range. And that is pretty much it. And the relative error formula is the same as it's always been. So we'll have the x new minus x old absolute times 100%. And you keep doing that over and over again until you get your error within an acceptable range. So basically all you need to do is isolate for your different variables in your n number of equations, and in this case it's a 2x2 matrix, so we have two equations So we're just going to have our x1 and x2. So it's pretty simple, and that's why I like it more than the Gaussian elimination. So let's do an example. All right, so this is our system. This is our A matrix. This is our X solution vector, and this is our C. So what we want to do, we want to solve for our X vector, right? So what we need to do, we need to rewrite this in equation form, which is always going to be the first step, right? So remember that, rewrite in equation form. Okay, so this is what it should look like when you rewrite it in equation form, and now we want to start isolating for our variables. So the first one, with our first equation, we want to isolate for x1, second equation, isolate for x2, third equation, x3, fourth, x4. I remember every time we move down our equations, we need to update our x with the previous calculation. Alright, so the first one, if you isolate for your x1, you get x1 equals 3 minus x2 all over 3. And I forgot to mention that our first guess of x is going to be at 0, 0, 1, and 1. So something like this will usually be given if you're writing a test. Let's say, okay, start at, x vector equals this or whatever, or there'll be enough information where you can make that decision on your own, which would be the most convenient to start at. So in this case, we're going to start x1 equals 0, x2 equals 0, x3 equals 1, and x4 equals 1. So that's our initial guess. So now in this case, we can see that plugging in x2 as 0, our x1 is going to be equal to 1, right? And now isolating for our x2 from this formula up top here, the second formula isolating for our x2 is going to look like this. 6 minus x1 minus x3 all over 2. So plugging in our values, now remember, we've just solved for our x1. Our first guess showed x1 equaling 0, but now since we've solved x1 to be equal to 1, that's what we're going to use for our second iteration, or sorry, our first iteration with our x2. And then our x3, because we haven't solved for anything yet, that's still going to be our initial guess as 1. So this gives us x2 equals 2. So this is pretty simple. x3 isolating from now the third equation. This gives us 9 minus x2 minus x4 all over 2. Now remember, we just solved for our x2 now. Instead of our initial guess of 1, or nope, our initial guess of 0, we're going to plug in our 2 that we just calculated. And x4 is still 1 from our initial guess. And this gives us 3. Now finally x4, we're going to look at our fourth equation of our system. Isolate for our x4, 11 minus x3 over 4. And remember, we just calculated our x3, which equals 3. So 11 minus 3 over 4 equals 2. So that is the first iteration. So on a test, usually it'll be like do 2 or 3 iterations, or do iterations until we're in an acceptable range within your error. So with that, let's calculate our errors with our x1, x2, and x3. So we can now say that, okay, subscript 1, we'll say x1 as for saying our first iteration. So x vector 1 equals 1, 2, 3, 2. So this is our first iteration of our matrix. And let's calculate our errors. So error 1, we're looking at our first component, our x1. Remember the formula? So that equals 100%. So that's a pretty big error. That's a huge error actually. So obviously that's not going to be very good, but we have to keep continuing on and calculating all of our errors. So our error 2, now we're looking at our x2 and we're calculating the error associated with this. So that one's also 100%. So that is huge, and that's no good. But let's just keep on doing it. So I'm just going to go ahead and calculate our error 3 and error 4, and I'm sure you guys could fill it in. Okay, so we got 100%, 100%, 67%, and 50%. So within this method, we always go with the larger error percent. So no matter what, say even if you get a tiny error with say x4, say you get 1%, but x1 is 100%, for example, you still have to say, okay, the associated error with the first iteration is 100%, and you have to keep going until the highest iteration is within an acceptable value. So in this case, we have two 100s, so 100 is our highest, therefore 100 is the first iteration error, and that is bad. So we need to go ahead and do a second iteration. So now remember, our x is now 1, 2, 3, 1 because we've just solved for those values, or sorry, 1, 2, 3, 2, because we just solved for those values using our first iteration. And now for our second iteration, we're literally doing the exact same thing with the same equations. So we know that our x1 is still 3 minus x2 over 3 because that's what we solved for from our system of equations. But now our x2 is our new guess, or our new estimated values. So this is 1/3. And same thing, x2, we're looking at the exact same formula that we did earlier from our original system of equations, but now we've got our x1. It's not 1 anymore, it's now our new calculated value of 1/3. So every time it's got to update it to the most recent calculated value for every iteration. And our x3 is the most updated value that we know of as 3. Boom. Simple. Alright. 1.33. Now x3, same thing. Original formula from our system of equations, 9 minus 2x minus x4 all over 2. Use the most updated values that we have. x2 is 1.33. It's not 2 anymore. And x4 is still 2 though, because that is the most updated value that we have. And this gives us 2.833. So now our x3, we just calculated our most updated value is 2.833 all over 4. And this gives us 2.04. Okay, so this is our new x. So let's call this x iteration 2. This equals 1/3, or 1. Remember, we got 1/3 is our new value minus our old one, which was just 1 from our previous iteration for 100%. So we've got 200% now. So it has increased. Our error for our relative error for our first variable, our x1, has now increased. It's doubled. So it may seem now like we got a diverging solution, but we'll do one more iteration and we'll really see if it is going to be diverging or if we can actually get a converging solution. So let's just do our error number 2 and see what we get. So 1.33 was our new calculated value for our x2, and our old one was 2. So error 2, well, that's good, it's gone down, so it is now 50.4%. So that's not bad. That's healthy. That's what we want to see. That is gluten-free, some would say. Healthy. So E3, error number 3, absolute value, our new value 2.83 minus our old one, which was 3, all over 2.83. Value times 100% equals roughly 22%. So that's going down. So that is good. Now we've got something converging. So that makes me feel a little bit better. So E4, our new value is 2.04. Subtract our old value of 2. That's good. So that is 2%. So that's tiny. That's perfect. But now you can see we've got something as low as 2%, as I was talking about earlier. But we still can only say that because our highest associated relative error is 200%, the second iteration error is 200%. So that is not acceptable. Let's do one more iteration. Let's do a third iteration, and hopefully we get something a little bit better. So now we know our x2 from our second iteration was 1/3, 1.33, 2.83, 2.04. So now we need to solve for x 1 for our third iteration. So if you remember, this equals 3 minus x2 over 3. And we know from this method that we have to put the most updated value that we have into our x2, and that happens to be 1.33. 3 minus 1.33 divided by 3, this gives us an x1 of 0.56. So you guys got the hang of this now. I'm just going to quickly write out x2, x3, and x4 and let you guys solve for those yourselves, and just remember that you have to use the most updated values. Okay, so now we got x3 equals 0.56, 1.31, 2.83, and 2.04. So that is our third iteration of our x. And now we need to calculate our errors, our associated errors. So E1. Boom, there we go, 40%. So that has definitely gone down. That is good. So we're starting to converge. So that's what I like to see. E2, 1.5%. Nice, that's good too. It's going down, guys. This is awesome. This is healthy. This is gluten-free. Okay, so this is going to give us a 0. See, this is why maybe I should have carried a couple more decimal places. So let's just, if you do the actual calculation, we get 2.825. So I should have carried more decimal places, so this will give us a little bit more accurate of an answer. This is getting so close. They're so convergent that we actually need to carry more decimal places. So that's a good thing. Gives us a more accurate answer. Yeah, so that is 0.3% relative error. Now number 4, hopefully it won't give me a 0. So we got to carry more decimal places on this because our error is getting so close. If we carry more, we got 2, 4, 3, 8. So let's use that. 2.0438. So that's what happens when you get closer and closer and closer. Your error becomes closer and closer to 0, meaning that you're converging to the correct solution. So that is a good thing, but I guess just make sure that you carry, enough decimal places. Yeah, so that is a 0.2%. So this is really good, but still remember, because 40% is our maximum, we can still only say that the third iteration error equals 40%. So, I mean, we could keep going until we reduce that. It's probably going to reduce even more because it went from 200% to 40%, but I've done 3 iterations. You guys get the point. I'm not going to beat a dead horse. You understand how to do this. You basically just want to do iterations, update your numbers, calculate your errors, and see it converge. So I was talking about converging and diverging, so let's just talk about what that actually means. So we can say a matrix is convergent if it is diagonally dominant. So what does that mean, diagonally dominant? All the diagonals in this matrix we can see is 3, 2, 2, and 4. Those are the diagonals. Now, a diagonally dominant matrix will look at the diagonal of the matrix, and it has to be greater than the sum of the remaining components. So 3 has to be greater than 1 plus 0 plus 0. 2 has to be greater, we can say greater or equal than 1 plus 1 plus 0. 2 has to be greater than or equal than 0 plus 1 plus 1. And then the last one is 4 has to be greater or equal than 0 plus 0 plus 1. Okay, so we can see in this case this is true. That is greater, okay? 2 is greater or equal than 2. 2 is greater or equal than 2. And 4 is greater or equal than 1. So we can now say that this matrix will converge because it is diagonally dominant. Now keep in mind that if any of these is not true, then we can't say that this is a converging matrix. So even if you have 3 that are good, if one of them, one row diagonal is not greater or equal than the sum of the remaining components in that row, then we don't know if it is convergent or divergent. We just have to say we are not sure at this point. If all of the rows, if this is true for every row in our matrix, then we can say that it is diagonally dominant and it is a converging matrix. So it will converge to a solution. So just keep that in mind. And that is it. That is the Gauss-Seidel method. So that is just another method to solve for our x vectors with a system of equations. So you can solve this with the Gaussian elimination, and you'll see that you do get the same answer. It is literally the same thing, just a different method on getting the same solution. So thanks for watching. If you like my content, like my videos, subscribe to my channel, share with your friends. Gluten-free learning. It's awesome, it's healthy, it's good for you. Actually, I kind of like gluten, but I like my stuff. Subscribe to my channel, share with your friends. Thanks for watching.